Hey everybody, welcome to example 2 on page 11. We're going to calculate a derivative using our theorem we just learned about, which tells us how we can efficiently calculate a derivative for a parametric equation, and we're going to use that to find a critical value on a parametric curve. So what we have here is a couple of parametric equations. X of t is 4t plus 2. Y of t is t cubed minus 3t squared plus t, and we are looking only on the interval from 1 to 7. So this curve draws out over our parameter values from 1 to 7. So remember, we have dy dx, and we're going to use our formula here, y prime of t over x prime of t. So that's the derivative of our function, and we see that y prime of t is the t cubed minus 3t squared plus t, so its derivative is 3t squared minus 6t plus 1. And that's over the derivative of x of t, and x of t is 4t plus 2, so its derivative is 4. Okay, now to find critical values, we're looking for values where this function is equal to 0. Critical values also mean they could be points where the derivative doesn't exist, but this is a polynomial, so we know the derivative exists everywhere. So to find our critical points, we just need to set this equal to 0, and then find out what values of t will solve that equation for us, and then make sure they're in the interval 1 to 7. So that's our job here. So we set our function equal to 0, and now noting that this is a fraction that is equal to 0, the only way that that's going to be true is if the numerator is equal to 0. You can also multiply both sides by 4. You can think of it that way. Either way, our first equation here is equivalent to just that numerator being equal to 0. Okay, unfortunately, this quadratic does not factor, and we're going to have to use the quadratic formula to find our values t that solve this equation. So we're going to set that up. We've got t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Sung to Pop Goes the Weasel, if you like. And a here is 3, b is negative 6, and c is 1. Okay, so now it's a matter of just being careful, putting everything in the right place. We have a negative 6, which is 6, plus or minus 6 squared, which is 36, minus 4 times 3 times 1, which is 12, all over 2 times 3, which is 6. And then we note that 36 minus 12 is 24. That can be written as 2. That can be cleaned up a little bit. It could be written as 2 times the square root of 6. So I'll just do that. I like to get it as simple as I can. 2 times root 6, did I say? And then over 6. And then that simplifies slightly down to 3 plus or minus root 6 over 3. So this represents 3 plus the square root of 6 over 3, and 3 minus the square root of 6 over 3. And now is when we probably should get out our calculator to find out which, if either, of these values are in our interval 1 to 7. So if I pop that 3 plus square root of 6 over 3 into my calculator, I think what I get here is 1.816, and then if I subtract square root of 6 from 3 and divide by 3, I get 1835. Okay, so clearly only one of those values is in the interval that I want, and that is 1.816. So I'm going to cross that second one out, and we have our critical value. Now, to get a critical point on the graph, I can plug this t value in to x of t and y of t to get those values. And I think for the purpose of this video, I won't do that. I will just leave it at that. It's not exactly important what those output values are, but if I needed them, that's how I could get them. I could plug them into each one of my parametric equations. All right, so that's how we find some critical points of two parametric equations. And the next video, we'll find an equation of a tangent line to a parametric curve. So I'll see you in that one.